Welcome back to Gabversity, where facts care not about your feelings, or my feelings, or anyone's feelings. Captain Deltron, the man of the hour, is back again. So we are going to talk about stellar evolution. Now, I never plan this correctly. It happens every time. Let's try and make this work. Hey. I like the kick. Let's see if this works. Does this sort of work? That sort of works. Okay, let's see if this works. Alrighty, so let us talk about stellar evolution. Now, what are we going to talk about in this reboot? In this reboot, Jada Diva, we are going to talk about the triangulation method, the astronomer's triangulation method, parallax and distance, and proper motion. It's going to be a lot of fun. So, let us begin. Properties of stars. We already have done in the last lectures figuring out surface temperature, chemical composition, and surface density, right? And we haven't done the mathematics of it, we've done the concept of it, right? In this chapter, we'll learn how we can determine distance, luminosity, radius, and mass. Tangents. Bon Charlies. Welcome back. All right, so distances to stars. We are going to talk about the trigonometric parallax. Okay, 1 parsec is 3.2 light years. Now, how does that even work? Well, what happens is that you have a star and you have the Earth, distance not to scale. Okay, now the Earth is going around in its orbit around the Sun. So as I do that, imagine relative to the Earth, the star is going to be doing this. Okay, now we're going like this. That actually forms a triangle. So what happens is we get this, my friends. Now, where is my magnifying glass? I will show this to you. What you can see right here is, can you see that? So, here is the star, and here is Earth, and Earth, as it goes in its orbit, actually shifts relative to the star's position. And that shift causes a triangle. So that triangle, my friends, just like trigonometry, that's where you get the word triangle, trigonometry. So you can figure out that if you happen to move a certain distance, right, the star shifts. So if it shifts a little bit, then it must be really far away. If it shifts a lot, then you're really close. Obviously, look, I'm really close to the phone. So if I move in my orbit, I'm moving across the phone. If I'm really far away and I'm moving, I don't move as much relative to the phone. Okay, same deal. So the equation for that is d equals 1 over p. So the distance is 1 over the parallax. And the parallax is in arc seconds. And what does that mean? It means that on a degree, right, we're looking at this star and we're shifting. How many degrees does the star shift relative to how far we've moved? Right? That's a pretty standard trigonometric stuff. So what I'm going to do now is I'm going to hold the phone upwards. Fingers crossed we're all the same now. And then I've got my astronomy book. Found it. And I can start drawing for you. Here is what's going on. Lovely to see you. We have here, whoopsies. Okay, we have the star. And here is Earth. And Earth is sort of going around its orbit, right? It's going sort of around like this all the time, right? Hey, Lula, welcome back. Now, I remember your actual name was Carol, I think, if that's right. Okay, so look what actually happens with the Earth relative to the star. It goes around and it ends up doing this. So here's the distance, right? And then the Earth shifts. Hey, welcome, excellent. The Earth shifts this way. So now the Earth is here, right? And now it's caused this parallax. So that parallax is an angle. And that distance here is a line. So look what happens. We can now see that this distance and this distance is part of a right-angled triangle. And if anyone's ever done high school trigonometry, you know that this distance over this distance, all right, is going to be the sine of this angle. So sine of the angle, which is this angle, equals this side, let's just call that A and call this side C. And now it's decided to do its thing. Come on, come back. You can come back. There we go. Equals A over C. So which implies that the distance, right, this distance c is going to equal a over sine theta, right? It's just trigonometry. Well, there you go. There is the formula. The distance, where's my magnifying glass gone? I was just holding it. Where did it go? Ah, there it is, sorry. All right, so as you can see right there, that the distance is 1 over p, and p is the angle, right? Because all they did was they just normalized it. So what does normalize mean? They're like, well, let's get a distance. Let's actually fix the distance, right? So we will say that the Earth moves a certain distance in the orbit, and it's going to make the triangle a 1 unit triangle. And then that way we can figure out the distance once we've actually created the triangle. So we in our orbit are creating the triangulated path, right? Because we're here we are, right? You and I are facing each other, and then as I move, there's now an angle this way, okay? So that angle and this create a triangle, and that's how we do the formula. Sorry, did you call me? No, no one called me. Okay, so there is a parallax of 0.76 arc seconds. Now, what's an arc second? Well, how many arc seconds are in an arc minute? 60. There are 60 arc seconds in an arc minute. And how many arc minutes in a degree? I think it's 60. Now, I might be wrong on that. We haven't gotten that far. All right, so let us have a look at that. It's right here, my friends. All right, come on. There we go. So, as you can see, the distance, Alpha Centauri, has a parallax of 0.76 arc seconds. So for the 1 unit triangle, right, the difference that the angle makes when we travel that 1 unit, right, the angle to Alpha Centauri actually becomes 0.76 of an arc second. So this thing here is 0.76 of an arc second. So sine of that, right? So therefore, we are going to get that the distance is 1 over 0.76, which is 1.3, which equals 4.3 light years. So that's it. So we know that this line right up here is 4.3 light years. And that's all it is. So it turns out, Dennis R. Hands, welcome back, my friend. Sooner gone. More of our intellectual giants are back. All right, so as you can see, this only works if the distance is less than or equal to, hello, my friend, less than or equal to 50 parsecs. This is something, my man, right back at you. Now, for anyone who doesn't know, Dennis R. Hands is actually a great astronomer and knows quite a lot of stuff. So he can always fill in the gaps. This method does not work for stars further away than 50 pc, and that's just quite simple, because when the stars are so far away, when you move that distance, it's very hard to get the angle accurate, right? Because it's so far away that you have to move so far to actually get a proper angle that you've already done in orbit. We're not going far enough. So that's what's going on, okay? And that's pretty simple. That's the same as saying, like, you know, if you're trying to look at a mountain, you know, that's like, you know, 100 miles away, right? It's going to be very hard that if you shift, you know, this way and this way, the mountain's not going to move very much. So it's going to be very hard to see how far away it is. So obviously that technique does not work when you get more than a certain distance. All right, now let's look at the proper motion. Proper motion, right, is the actual motion of stars throughout the Milky Way. So the stars themselves are physically moving, and that happens. For example, the constellation, I'm trying to think, when you go back in time, right, the stars were not where they are now. So there are lots of, for example, constellations that we can't see today that our ancestors could see. In the same way that in the future, any descendants of humans that are still around somewhere will not see many of the galaxies because they would have disappeared beyond our observable horizon. So I'll show you over 100,000 years. So 100,000 years ago, this is what the constellation looked like, right? This one here, okay? This is the Big Dipper. So this is what it looks like today, right? That's the Big Dipper today, okay? But that's 100,000 years ago. Look how different it looked. You can see that the top here was flattened, right? And this part here was like that. So this star had moved. It's a big time frame, all right. If you're looking back, it's not that big. Like for our lifespan, it's big. But yeah, if you go far, and then in the future, it's going to look like this. So it's going to be shifted upwards, and this will be shifted up. So if you're trying to, for example, like, you know, a lot of biblical archaeologists are working with astronomers to figure out where the stars were, small time for universe. Exactly. Dennis R. Hand's, his first appearance. Okay. They're trying to find, you know, like where the star would have been for the Persian Magi who were wandering over to see this supposed newborn king, if that's true or not true. And they were figuring out which star would have been the northern star or whatever it was, the bright star in the sky that they were following to get to Bethlehem. So from an archaeological perspective, it's important. 2,000 years is small. You'd think so, but it's 2% shift. And a 2% shift in a star is pretty massive, right? Because they're so far away, and from the Earth, if it shifts 2%, it's going to completely destroy where the star would be, right? It wouldn't be, for example, over, I don't know, like it could be the wrong country, right? Like it might look today like it should be over freaking, I don't know, like Iran somewhere, but back then it was over Israel. You don't know, but yeah. Okay, so flux or brightness. Flux or brightness. All right. So flux has to do with two-dimensional energy release. So I'll give you an example. If you open your window and a blast of wind comes through, you could analogize that to flux, because the window is a flat two-dimensional surface and there is a blast coming through the whole window. 2 degrees of a circle is small. Depends on how big the circle is relative to us. But yes, good point. All right, so flux is in joules per squared meter per second, right? So it's how much energy is radiating off a surface over time, right? Which is, and then we've got the magnitude scale. So this was actually, I've said this before, don't Brahe or Kepler notice star move from ancient Greeks? How funny you just said that. I was just about to say that. How funny is that? So Hipparchus is the one who came up with the magnitude scale, and that was in 160 BC. It goes to show you, we think we're smarter, man. We're not smarter at all. We just have better technology. Yeah, amazing, huh? Amazing minds. So first magnitude stars are 100,000 times brighter. Sorry, 100 times brighter, which is 100 times more flux. Now, what's interesting is that it's actually, what do you got here? A 2.512 change in apparent brightness or flux. And there is a reason for that. There's a mathematical formula which we will get to. It's got to do with the ratio of 2.512. On the shoulders of giants stands Dennis R. Hands. Absolutely. All right, this one is one of our first ever formulae. They're all basic stuff in this course. They're all just trigonometric stuff, logarithmic powers, like high school mathematics, basically. All right, so I'm trying to hold the magnifying glass and do this at the same time. This is not easy. That is not easy. All right, so here we go. Sorry, I will get better at this. All right, the apparent, I've got to hold the pen and the magnifying glass together. I think that's the only way it's going to work. Unless I just it's not working. All right, so the apparent visual magnitude is called MV. All right, a number which can be used to compare apparent brightnesses. All right, this is, I'll explain what this is in a sec. It actually is from over here. If you look here, right, you can see that, you can't actually see it, but that's a little kid on a bike, and that's a pickup truck. And even though the pickup truck's light is gigantic compared to the kid's bike, from this observer, lowercase m, exactly. Thank you, as always. I love having Dennis here. It's always makes it better. The observer sees these two lights as the same. So they have the same apparent visual magnitude, even though one's by a pickup truck and one's by the kid on the bike, because of the distance away from the observer, right? So both stars appear equally bright, although if you look at Earth, look how small star B is compared to how massive star A is compared to Earth. But that's because that one's so much further away. This is called the apparent visual magnitude would be equal. All right. Now, this has to do with the flux. The fluxes F and A we receive on Earth when the two stars are related to their apparent magnitudes. All right, so here we go. So this is how it works. As I said, 2.512. Flux A over flux B right, is related by 2.512 to the power of the apparent magnitude of A minus the apparent magnitude of B. Okay, now what does that mean? Well, that means that if the apparent magnitudes are the same, then MB minus MA, so the apparent magnitude of B minus the apparent magnitude of A is going to be 0 because they're the same number. And 2.512 to the power of 0 is 1, which means that the flux of A divided by the flux of B equals 1. And when does that happen? That only ever happens when FA equals FB, right? In other words, they have the same flux coming to Earth. Ginny Lee, lovely to see you. All right, so that's more of a mathematical version. I'm not getting too heavy into the maths in this lecture, all right? But you can rearrange these as well. I'll show you. Okay, so the same deal here. You look at this. That flux divided by that flux. If they're the same, then that divided by that is 1. Now, if anyone knows, the log of 1 is always 0. So 2.5 by 0 is just 0. Now, why would MB minus MA equal 0? Because they are the same. And the only way they are the same is if their apparent magnitudes are the same. So from this mathematics, we now have a new rule. More witchcraft, damn straight. This time it's to do with planets. The rule is this. If the flux from two different stars, no matter how big they are or small compared to each other or to us or anything else, if the flux coming to Earth is the same, then that has to mean that the magnitude, apparent magnitude, or the apparent brightness of one star is exactly the same as the apparent brightness of the other. So if you see two stars in the night sky that have exactly the same brightness, it could be that they're the same, identically the same star, or it could mean that one is a lot further away than the other, but it would have to be bigger, okay, or brighter. Bingo. Dennis is already on the money. All right, so what I'm going to show you guys is an example. All right, so have a look once this decides to fix itself up. There we go. So this is Rigel, magnitude 0.14, Betelgeuse, right, 0.41. Okay, for an apparent magnitude difference, so that's 0.41 and that's 0.14 for Rigel, okay, two different stars. Now, the apparent difference in magnitude is 0.27. The intensity ratio is have different brightness based on their composition. Absolutely, my friend. Absolutely. So then what would happen is that this equation, if that was true, then this equation would have would not equal 0, right? So this divided by this would not equal 1 because they would have different fluxes if they were the same distance with different brightnesses, yes. So we find an intensity ratio of 2.512 to the power of 27, which is 1.28. So that means that Rigel has the lower number than Betelgeuse. Hey, Liran, welcome back. So here we have Rigel is 1.28 times brighter than Betelgeuse, okay? Because 2.512 to the power of 0.27 is 128. So that means that this has a magnitude of 0.14. This has a magnitude of 0.41, which means Rigel has a 1.28 times more intensity in terms of ratio than Betelgeuse. Okay, that's it. That's all it is, my friends. So the next one, the brightest star in the night sky that we can see is called Sirius. The weakest star is called Joking. Now, that's obviously a joke. All right, Sirius. Are you serious, bro? Yeah. So Sirius, Sirius. It is the brightest star in the night sky with an apparent magnitude, MV. Remember, MV, lowercase m with a small v, that's apparent magnitude of negative 1.42. Because the more negative you go, the lower you go, the brighter the star. All right, the full moon has an apparent magnitude of negative 12.5. Right, so negative 12 is much lower than negative 1, so it's way, way, way brighter. Now look at this, the sun has an apparent magnitude of negative 26.5. So the sun is only double, right? It's only double the moon. And look at the difference. Look at the difference between the sun, which has roughly double the moon's apparent magnitude, and it freaking, like, look what it does compared to what the moon can do. So imagine that gives you an idea of when you're doubling the magnitude, you are intensifying the light by a huge amount, by like thousands of times. Just like decibels with sound. You know, when you go from 1 decibel to 2 decibels, the sound is going up exponentially, right? Because it's a logarithmic scale. But anyway, exactly, exponential. That's exactly right. Okay, so the next, brightness and distance. So we just said the flux, right, is related by the distance. Of course, it has to be, right? Because that's why you can have the same flux from 2 different sized or 2 different brightness levels because of the distance away. It's adjusting. Obvious, right? Like if you have a radio on really loud next door and there's a radio on really quiet here, you could probably hear the quiet one more than the loud one because the loud one's further away. It's exactly the same. Right, so MD minus MD2. Okay, D1 over D2. So the flux is proportional to its intrinsic brightness or luminosity, and inversely proportional to the square of the distance. All right, so as you get further away, right, it is proportional to the distance squared. In other words, the sound, right, magnifies like double. Let's just say, no, if you bring in the distance, like if you double the distance inward, then the brightness goes up by 4 times, roughly. It's a ratio, right? But you're looking at a factor of 4 because it's squared of the distance. Okay, so if you say double the distance, then it's going to be a quarter of the brightness. Mizrahi Israel, hello, or Mizrahi Israel, depending on where you're from. All right. So as we said, MD1 minus MD2 is 5 log D1 over D2. And I'll show you what I mean. Have a look. MD, okay, let me get a double the distance equals brighter lights, big dicks. Your timing is unbelievably perfect every time. I tell you, the guy is a whack job, but I gotta give it to his timing. It is perfect. God, that is too good. Timing is too good. That's why I never block him. He's just too good, his timing. All right. He just waits for the right time. Anyway, all right. So we have here the magnitude of the first minus the magnitude of the second star, right, is the same as saying 5 by the log of the distance of the first over the distance of the second. Okay. Now, why is that important? Well, obviously, if we have the distance and we have one of the magnitudes, we can find the other magnitude. And this is an intrinsic brightness. So we can find the actual brightness of a star. Why is that important? Well, obviously, if we know the brightness, we can find out the temperature, we can find the composition of the star. So here, absolute magnitude. The magnitude of a star would have, if it was a distance of 10 parsecs. Okay? Now, if anyone remembers, 10 parsecs is probably around 32.6 light years or something like that. Okay? So that what we do is we say, what would happen if all of the stars that exist were all at an equal distance away from Earth? So then we have like an actual standard set, right? So for example, let's standardize big dicks. So we'll have a standard size. Oh, it's too funny. Too funny. It's so ridiculous, it's funny. All right, so here we go. So 5 log the distance over 10, okay, is too many variables. Well put, my dear. Equals small magnitude minus the absolute magnitude. So this here is the apparent brightness minus the actual brightness. Now, how can you tell that this works? Well, if there was a star that was actually 10 parsecs away, which is around 32 light years, right? If it was that far away, well, then that divided by that is 1. Log of that is 0, which means that the apparent brightness has to equal the absolute brightness or magnitude. That's the only way that this would equal 0. They have to equal each other, which means if those two equal each other, then it also means that the star is 10 parsecs away. So that's how you can find the distance of the star based upon its magnitude. If you know its actual magnitude and its apparent magnitude, you can find how far it is away. Or conversely, if you know how far it is away, you can find its absolute magnitude, or you can find this one here, which is -5 plus 5 log 10. Okay, so now this is really good too, because if you don't know this, if you only know this, well then you could solve it to find out the absolute magnitude. So for example, right, the relative magnitude minus absolute magnitude equals -5 plus 5 log 10. Okay, well then that implies, right, that the absolute magnitude of a star is going to equal the apparent magnitude. Come on, bastard. I just put the equals. It equals the apparent magnitude, and we just put this over this side, plus 5 minus 5 log 10. All right. So there you go. So now, if you have if you get a telescope at its finest, there you go. So if you get a telescope and you get an apparent brightness of a star, you can find its absolute magnitude by using this equation. That's it. Just a basic algebraic equation can help you find the absolute magnitude of a star. And you can plug that into Excel. If you put that formula in Excel, then what you can do is get every single star, which they've done, but with like hyper performance computers, right? And you can then get the actual absolute magnitude of every single star you want. And then you'll know which stars are radiating more light. So you can classify stars by which radiate the most light, etc., etc. It's great stuff. How we with mathematics can manipulate the universe. Axis shifts affect this equation. Good question. It depends on which axis. So if you, from Earth, if you're looking at it, the brightness will not change enough for that to be a problem. And that is why they set the standard as 10 parsecs away, because it's so far away from Earth that Earth's orbit will barely make a difference to the brightness of the actual star. But good question. Okay. Luminosity, absolute magnitude. Okay. So let's have a look. This is quite interesting. The luminosity of Betelgeuse, right, is negative 5.5. That's the absolute magnitude. But the absolute magnitude of Rigel is negative 6.8. Okay. But the apparent magnitude, right, the apparent magnitude is that Rigel is 0.14 and Betelgeuse is 0.41. Now, why is that the case? That is the case because Rigel is further away from Betelgeuse. So Rigel is 244 parsecs away, right? Whereas, so it takes about, 700-800 years to reach us. Betelgeuse is only 152 away. All right, so have a look at that in the sky, right? So you can see there's. Oh, let's wait for this to focus. There we go. So there's Betelgeuse and there's Rigel, right? You can see that Rigel and Betelgeuse, Rigel actually looks much brighter than Betelgeuse, right? But it should actually look even brighter, but it doesn't, and that's because it's further away. And you can see that the difference in absolute magnitude is 1.3. So the luminosity ratio is 3.3. Now that's different to what we said before, right? The absolute luminosity ratio is 3.3 times different. So Rigel is actually 3.3 times brighter than Betelgeuse. All right, so it's 3.3 times brighter. But on the last page, we just did the equation. Rigel only looks about 1.4 times brighter. Now, why is that the case? Well, because Rigel is further away. That's it. Pretty simple. All right. The Balmer line, not the Obama line, the Balmer line. Okay. This is really important. Why? Because the Balmer line, based upon quantum mechanics, you can figure out the fingerprint of every star's emission of electromagnetic radiation that reaches us. And using a computer to analyze the lines, right, because of the specific quantized manner with which stars emit radiation, because we live in a pixelated universe. So based upon which pixel is reaching us, we know what type of star it is, right, or what it's emitting. So it's pretty crazy. I'll show you. So you look at Ernie Banks, right there, okay? Balmer line strength is sensitive to temperature. Actually, you know what? I'm going to try doing something. Let's see if this works. I don't think that's going to work. No, that's not going to work. All right, I give up. Okay, so this is too small. See if I can make it bigger. Can I make this bigger? All right, most hydrogen atoms are ionized, weak Balmer lines. That's at a lower temperature, okay? Sorry, it's a higher temperature, sorry. As the temperature drops, so this is above 10,000 degrees Kelvin. As the temperature comes to about 10,000, right, then we get a beautiful, strong hydrogen line right up here. That is the line strength. And the line gets weaker and weaker as the temperature goes down, okay? Here, there's not enough energy for the hydrogen electrons to pop up into new levels, okay? So I'll show you what I mean, right? Let's just say here's a hydrogen atom and here's the electron. When you inject this amount of temperature, it's ideal, it's Goldilocks. So you inject the temperature into here and it gets excited, hey, hey, hey. You inject the big dick, or, you know, as that guy likes to say, and then the electron comes out here, okay? So because it comes out here and then it falls back again, it emits light radiation. And that light is what comes to us, okay? Whereas on this side, there's not enough energy. So the hydrogen sort of just stays, I know it's terrible. The hydrogen stays here, so there's not much light at all coming to us. And that's why it's weak. Here, there is so much energy that the electron gets blown right off the hydrogen itself. So then you also don't get much. Okay. So when you get really strong hydrogen waves, you know that the temperature of that star, the surface temperature, is probably around 10,000 degrees Kelvin. Right? Very important. What's that? 5 plus 32. Probably around 15,000 degrees Fahrenheit, roughly. Probably a bit less. 14,000 something. All right, so in other words, you got the electron, you give it too much power, and it just blows right off the proton. If you don't give it enough, it's just like, whatever, I can do better. Yeah. And then you get it just right. Okay, so measuring the temperatures of stars. Comparing line strengths, we can measure a star's surface temperature. Okay, now here's what's interesting. That was just hydrogen. There's also other stuff, right? There's also helium, iron, calcium, titanium. All of those that get excited, they require different energy inputs. So depending on which ones are getting excited at different times, you know what elements are on the star, but you also know the surface temperature of the star. And that's how we figure it out. All right, spectral classification. This one is confusing because it's a graph that has like it's a box graph. It's very weird. Have a look at this. Stoner, secret agent Stoner, awesome. All right, have a look at that. So here you can see that you probably can't see that, but that's O, if it decides to actually focus itself, OBAFGKM. Right? OBAFGKM, and then there's different numbers or degrees within each of the letters. Okay, O is the hottest, M is the weakest, and this is the temperature. So obviously up here is O level. And then this is the wavelength of light that reaches us. So it's a weird graph, right, to read because it's actually a 4-dimensional graph squashed into a... All right, so here is how to remember it. Oh, be a fine guy, kiss me. Oh, be a fine guy, kiss me. Or, oh, be a fine girl, kiss me. Right? And that's the brightest. O is the brightest. B a fine. Fine is like, it's all right. Are you familiar with any corporate space programs? None that I can talk about publicly. Girl, guy, kiss me. Okay. So there you go. But you could also say only bad astronomers forget generally known mnemonics. That's another one. Or oh boy, an F grade kills me. I like the first one. Oh, be a fine guy, kiss me. All right, so there you go. Our star. Ooh, I can't remember. Oh, Gab. Oh, be a fine Gab, kill me. I think our star is a G star. It's a G star. Ghetto G star. All right, surface temperature. Okay. I'll skip that one. So, next, composition of stars. Composition, the Gab star. The sun. All right, so, composition of stars. Let's have a look at this. Hello, there's my fat face. All right, there we go. How am I going to get this? There we go. That's looking good. Hydrogen. All right, percentage and in the sun. This is the sun. So the sun is 91% hydrogen, 8.9% helium. But look at this. Even though it's 91% hydrogen, it only makes up about 71% of the mass. And that would make sense because the other materials are much more dense. So you got helium, carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, iron. These are all the elements in the sun. Look how much iron makes. Iron is only 0.003%, and yet it makes up 0.1% of the mass. So it goes to show you how much heavier or denser iron is than hydrogen. Pretty cool stuff. All right. So now I'm going to talk to you about the HR diagram, which is, the full name is the Hertzsprung-Russell diagram. I would have thought more sulfur. You know, that thought never occurred to me. All right. So, Hertzsprung-Russell diagram. Of course, someone with a name like Hertzsprung is going to make a diagram that is way too complicated for me to understand. All right, so since it is hot as hell. Gotcha. Hey, you're too quick for me. All right, the family of stars by the Hertzsprung-Russell diagram. Stars different temperatures, luminosities, and sizes. So to bring order into the zoo, we organize them in a diagram, which makes no sense to me. Absolute magnitude or luminosity is this way on the graph. Temperature is this way. Right? So if you have a low temperature and high luminosity, it's going to be there. If you're going to have a low luminosity and you're going to have a high temperature, it's over here. Right? So it's a multi-dimensional diagram. It's very difficult to understand. 15 miles down the road from where Elon's new industrial factory is going to sink his ship. Oh, that's too good. You have to scope from there, my friend. All right, and here is the diagram in 3D. So as the luminosity, right, increases, right, and here is the temperature increasing, and these are main sequence stars. So with main sequence stars, their luminosity is related to their temperature. Right? You can see, because as the luminosity goes down, so does the temperature. Here is our sun, right there. These ones are like ridiculously huge stars, like this one here. Huge luminosity, high temperature, just crazy. Fairer stars are here. Hotter stars are blue and lie to the left. More luminous stars are up here. And here you can see this star is brighter than a main sequence star of the same temperature. Okay, because here is the main sequence star, and this is above, right? So they're the same temperature, but it's brighter. So it falls outside of a main sequence star, which means it's not going to live as long. Okay, these ones burn up their fuel quickly. Mindtech Enterprises. I'm not familiar with them. I have heard of them, but you probably know more than me, I would dare say. Especially the more you get stoned, yeah. All right, so what can we tell you about these stars? The stars that burn more brightly or are more powerful or bigger than main sequence stars, they're like the ones that party all night. So they party all night, every day, and then they die very quickly, right? They age really quickly. And we spoke about why that happens. It's to do with the ratio between gravity and the burning of the fuel. All right. The brightest stars are blue, and sometimes they're red. They're quite pretty sometimes. All right. So the radii of stars in the 10,000 times the sun's radius, 100,000 times the sun's radius, as large as the sun, and it runs on an angle like that. Can you believe that? There are stars that have 10,000 times the sun's radius. How does that even make sense? How could you even picture a star like that to your work, possibly? Cool. That party too much, yeah. Exactly. Very true. I'll have a look at it. J. Essex. I'll have a look at that stuff. It's cool. Thank you very much. I always love input, man. It makes things so much better. All right, relative sizes. All right, get ready for this. I'm going to show you. Hey, Glogos, welcome back. So, I'm going to show you. Here are the relative sizes. Now, you can't actually see this, but this is for, I think that's Betelgeuse, but I can't tell. But look at that compared to our sun. Take care, my friend. All right, so look at that compared to that. That's just insane. I mean, can you imagine waking up and seeing the sun like roasting the earth? We wouldn't be alive, but anyway. So these are the supergiants, 1A. 1B are just supergiants. William Andrus, bright giants, giants, sub-giants, main sequence, which is us. Run along this line. So the giants are up there. Sub-giants are down here. Bright supergiants, 1A are up there. Okay. All right. So there you go. Our sun is classified in G, as I said, but it's G2. So it is called G2V or G25. Whereas the supergiant Polaris is still G, but it's G2 1B because it's a supergiant. Let me see how that works. It's crazy. Spectral lines of giants. Pressure and density in the atmospheres of giants are lower than in main sequence stars. Well, it's because they're so big, right? So the outer levels are so far away from the center that they're going to have much less density. From the line widths, we can estimate the size and luminosity of a star. All right, absorption lines in spectra of giants and supergiants are narrower. Distance estimate. Spectroscopic parallax. This is pretty damn awesome stuff. So absorption lines. So when you receive the light, you get little gaps, and the gaps are narrower in the supergiants. So this is how they find these things. All right, binary stars. We'll probably stop after this. We didn't get through much of it, I think. More than interesting. Most of my head, but I'm learning. Awesome. Oh, I'm glad. Thank you. You guys make it interesting for me. Otherwise, I wouldn't even read it. More than 50% of all stars in our Milky Way are binary stars, Cepheid variables. Stars are quite important for existences. That's too good. This is now like our running meme. Yeah, absolutely true. Yeah, we I think I was going to do it today, but probably in one of the upcoming lectures we'll talk about Cepheid variables. That's what she said. Too funny. More than 50% pairs or multiple systems of stars, right? So it's sort of like, imagine having, all right, so when I was 19, I was really, really skinny, and I dated this really large Pocahontas girl. I really liked her, actually. I was happy to stay with her, but she thought I was cheating on her, which I never was, actually, which is really funny. But anyway, when we would hold hands and, swing around, right, we are circling a common center of mass. Now, the center of mass is closer to her than to me because she has more of the mass of the system. And that's the same with binary stars. The big star, right, and the little star are swirling around each other. So that's sort of happening. Okay. Now, to estimate a stellar's mass, okay, this is now, we're going to have a bit of mathematics here, and then I think we'll stop because this lecture's gone on a bit too long. Estimating stellar mass. Not Stella's mass. Stella! Alright, stellar mass. A large Pocahontas girl. Yeah, well, she looked like I thought she was gorgeous. She looked like Pocahontas, but she was very large. But she was in shape. She was just a large girl, but she had a beautiful shape, like a nice hourglass figure. She was just very large, right, in terms of her size. And I'm like quite slender, right? And when I was 19, I was like really thin. So it was Amazon woman, yeah, something like that, yeah. Yeah, I thought she was awesome. But anyway, long story. All right, so let's go back to this Kepler's third law, okay? Now, py squared equals au cubed, okay? And what does that actually mean? Okay, P is the period, and A is the separation distance. And we're talking about binary stars here. So the period, right, it's not once every month, as some people might actually think. It depends on the star. So here is one star and here's another, and they're orbiting. Okay, and how long it takes them to do one full orbit is called the period. Okay, so that is the period squared. Okay, is A, and is the distance. A is the distance, right? So one solar mass in the center. We find almost the same law for binary stars with masses M and A different from one solar mass. So the mass of one star plus the mass of the other equals, okay, the distance cubed in astronomical units divided by the period in years squared. Now that makes sense because that's three-dimensional and that's two-dimensional. So when you divide that by that, you're left with one dimension, and mass is in one dimension. Right? It's called a scalar because it's in one dimension. All right, so there you go. That is our formula regarding constellations, Virgo and Leo of the stars. I tend not to work on belief, but it all sounds plausible. I guess we'll find out. You'll have to let me know because you tend to watch these much more closely than I do, my dear. So definitely let me know at Gabversity or tweet us at Gabsmacked. I'd be very interested. Okay, so how to estimate mass? Okay, well, we know, for example, okay, 32 years of separation of A, 16 AU. So what is this? Let's have a look. We know that the mass of the sun plus the mass of the earth is 1 AU, because our distance from the earth to the sun is 1 astronomical unit by definition. And it takes 1 year for us to go around the sun. So 1 divided by 1 is 1. So therefore the mass of the sun plus the mass of the earth equals 1 solar mass. Well, that's true because the earth is so much lighter than it's roughly equal to the mass of the sun because we're so small. So here, what happens if we have these two stars, right? And we know that it takes 32 years, right? So what I'm going to do, well done. So let's say we have here two stars, right? And they're orbiting each other, okay? So they're basically, this is going around, and this one's also orbiting around, right? So this thing is taking 32 years. So the period equals 32 years. Okay, and the distance from each other is 16 AU, which is 16 times the distance between the Earth and the Sun. So the distance in here is 16 times the distance between the Earth and the Sun. And we know that it takes 32 years for them to complete their orbit. So all you have to do is get that distance and cube it, and divide it by the period, Kepler's law of motion. Exactly, Drew is on the money. Divide it over the period, which is 32 years squared. So that cubed over that squared equals 4. So this combination of stars is 4 times the mass of the sun. Okay. So basically, when you have a binary system, if you know the distance apart between those two stars, and you know how long it takes for them to complete one period, then you will know their combined mass. And that's due to a modification of Kepler's law. Exactly correct. Okay. And I think we will end the lecture here. Whew. Any questions? Lovely to see everybody. If you have any questions, don't forget, you can tweet us at Gabversity, and we can answer them next time. And we only got through, geez, we did not get through much at all. Oh my God. There's a lot more to go. Honest, you did, my friend, you did. All right, well, all the best. I may do a quantum mechanics lecture next, but my voice needs to, when do we get our diplomas? Well, what's interesting is that for Patreon members, why, thank you very much. For Patreon members, I actually give them a test, and if they pass, then they can use that as a credit to go to their university. They will have to do a test at their university as well. But what can happen is that you can then get an automatic credit for the actual subject. So I've done this before. I do this with my language ones on Sixlang, Sixlang. When I teach languages, you can actually take what I've taught you and do a test I give you, and then go to a university. Nabil Assal. All right, Nabil, if you want to know about me, go to Gab Smacked on YouTube. Do I teach beginner trig? I do. For Patreon members, I teach whatever they want me to teach. GABSMACKED on YouTube. And there is a second live autism speech which talks about me and my book you can get at xlibris.com or Barnes & Noble or Amazon, and you can download the ebook for $5. Ernie Banks. What is the property of iron that makes it so much more difficult for the sun to fuse? Good question. It is the required energy. Do I teach sex ed? No, I would teach you all of the wrong things. But it is the required energy at a quantum level. And I actually talk about that in my quantum mechanics lectures. So if you want to stick around, it's actually this topic coming up, explaining why solids manifest in certain ways based upon their wave functions. And that is it. You know you are really smart, lol. Sometimes I'm smart. Do one on entanglement. I will be doing one on entanglement. How do we get a signed copy? Yeah, if you go to, well, if you you can buy one directly off me now. I can send you signed copies because I have them in stock. Within 10 days they'll all be here. So if you go to paypal.me/gabsmacked. Why were you laughing? I laugh for different reasons. Sorry, there's a delay, so I'm not sure. All right, I love you guys, man. I'm going to go and do a quantum mechanics lecture probably soon. Sprout in and out of here. Mwah, to all of you. You're great students. That's why. It's so much fun. Gab smacked. Facts don't care about your feelings.